Okay, so thank you everyone for joining. My name is Ben-Amir. I'm here to present my PhD study about the influence of additive manufacturing process parameters on the dynamic mechanical properties of aluminum silicon magnesium alloy. So I think we all know the benefits of additive manufacturing on its ability to produce very complex structure and rapid prototyping. And there is a lot of way to additively manufacture a component. We are investigating the SLM, selective laser melting approach, in which a laser is scattering and melting the thin powder of layer. Here you can see a demonstration how it happened layer by layer to get a 3D component. So this microstructure is very, very unique. You can see that we can see evidence of the melting pool and the melting pool boundaries. And from above, we can see evidence of the laser tract. And this melting pool boundaries is characterized by a fine and coarser cellular SI network. So my main objective of my PhD was to find a correlation, find the connection in between the scanning parameters, such as the laser adjustment and scanning pattern and post-processing, to the dynamic behavior and the microstructure and crystallographic orientation. And again, the idea was to find a connection between them. And as part of my PhD, we developed several experimental system. One of them that I'm very proud of is the dynamic shear punch assembly, which generates a pure shear stress mode in the specimen and can fit in any split Hopkinson pressure bar. And you only need the strain gauges to characterize and to measure the shear stress, normalized displacement, and normalized displacement rate. You can see that it built from the projectile, the specimen holder, and the disc specimen that undergo shear. This area, very thin area, is sheared under pure shear stress mode. And we validate this approach by using an LS-DYNA numerical model. And we took as a case study the aluminum 6061 T6 because it had no shear rate dependency, and his plasticity model and fracture model is very well known. And you can see here that in this small region that undergo shear, there is almost zero traxiality, in fact, zero traxiality for the most of the specimen that indicate pure shear failure. And we also validate the nominal results by comparing it to the ASTM standard quasi-statically and also dynamically. And we saw that it all aligned perfectly with the results known from the literature. And also, we can see here the comparison between the simulation and the measured strain from the strain gauges. You can see that the signal is free from reverberation and there is no oscillation. Therefore, the measurement is very, very accurate. We don't need any filtration for the results. And in fact, we can use those assumptions to measure the shear stress, normalized displacement, normalized displacement rate. Another thing that we build is a tension split Hopkinson bar, that what's new about it is we put it all vertically, and we put a lot of effort to get the right amount or the right size of a thread to connect the specimen to the bar. And again, we went into validation and verification campaign, and you can see here the results that is also free from reverberation. And unlike other results, we don't use filtration, so we can see a very delicate changes in between the samples. And in fact, we wrote another paper about how dynamic loading is propagated along different threads and find the proper way to use it in a split Hopkinson bar. So let me remind you my objective. We try to find a connection between the dynamic mechanical properties, scanning pattern, and the crystallographic orientation. And now I'm going to go over briefly the results, and then I'm going to show you the study that I'm going to focus on. So at first, we took two different scanning patterns. One is bidirectional, which the laser go back and forth in the long vectors. And the second one is chessboard, in which every island is scanned separately. And we can see that is affect greatly on the crystallographic orientation. You can see that there is much more pronounced, much more dominant texture in the chessboard strategy that affects the dynamic mechanical properties and the crack path. You see that in much more homogeneous texture, where the crack is much more deflection and and when the preferred crystallographic orientation, the crack is notching and just moving through the sample. Another thing that we saw or we investigate is the difference in between the core scanning and the shell scanning. And we saw that in the shell, this change in scanning is building much more porosity in the shell region. You can see indicating by the porosity in the outer radius, and that affects greatly the dynamic mechanical properties in terms of stress and in terms of breaking elongation. Another thing that we did is we tried to characterize the difference in between the heated building platform, the sample, the distance from the heated building platform, and compare it to stress relief treatment. And we saw that the density, as we go up, the density going down, and the micro hardness, we saw that as we go up, micro hardness going up as well. And stress relief treatment reduces the microstructure and level things up. So we saw the same trend in the dynamic mechanical properties, in which the highest sample reaches the highest amount of stress, and being close to the building platform act as a stress relief treatment. You can see here that they are almost identical, the lower sample and the one that undergo stress relief treatment. And the reason for that being close to the building platform or having stress relief treatment is breaking the SI network. And for the top sample, in the as-built condition, this network remain continuous and act as a strengthened mechanism. So in this point, we thought maybe we can stop measure every aspect, every parameter individually, and maybe we can take something in a whole. Maybe we can get a large number of parameters and then see what's happened. So we took the 5 most influential parameters: the laser power, the scanning velocity, hatching distance, which is the distance between the scanning vectors, scanning pattern, and the orientation. And we took each one of them in 3 levels, and we asked ourselves one major question: what is the most influential parameter, and how and why does it affect the dynamic mechanical properties? So if we will do 5 parameters in each level, 3 level each, and we have to do repetitions, so we get from around 1,000 experiments. However, if you use the Taguchi design of experiments, which the one we are using, we only have to do 27 sets of experiments, and if we do repetitions, we can only have 100 experiments, which is still a lot, but it's manageable. Here you can see the metrics of the design of experiments, and what we measure for each experiment is the maximum dynamic stress that this sample reaches. And we calculate the signal to noise ratio in the larger the better constellation to maximize the response. And what we can see is that the loading direction and the orientation is the most influential parameter. How do I say that? Because you can see that a slight change in the orientation will result the biggest change in the outcome, in the signal to noise ratio. So therefore, it's the most influential. So this result was not so surprise for us, because we saw that under all our study, under compression, under shear, and under tension, we saw the same trend of difference between those orientations. We saw that in general, the Z sample reaches a higher stress level, and the XY sample reaches longer elongation. So we get the how, but now we wanted to do the why. So we tried to quantify these results, and what we did is extract the microstructure for each sample And we calculate another thing that we saw, that the crack is propagate along the melt pool boundaries. Again, under compression, under shear, and under tension. You can see here that the evidence of the melt pool's boundaries. And we wanted to quantify it. So we expose the microstructure and we calculate the normalized crack path. What is this normalized crack path? Is the path that between 2 points regarding of the orientation that follows only the melt pool's boundaries. So we did an image analysis and took the first breadth first search algorithm to calculate the minimum line across those melt pools boundaries and divided it by the straight line between those 2 points. And what we get, you can see here. So we can see that as the normalized crack path or the normalized path is increasing, the dynamic stress increases as well. So we have here a heuristic model that can show these results. And the reason for that is from energetic point of view, because if the crack is propagate along the melt pool boundaries, so in the Z direction or in the 90 degrees direction, it needs more to deflect in order to propagate. So it has more way to overcome, and therefore we need more energy and therefore more stress. So in summary, we saw that the scanning pattern is affecting the crystallographic orientation and the crack path and the dynamic behavior, the plastic behavior. We saw that being far from the building platform increases the stress and reduces the elongation, and it's the opposite if you get close to the building platform, and because being close to the building platform act as a stress relief treatment. And we saw that the presence of the shell is contained with very much porosity, and therefore it reduces the dynamic mechanical properties. And from the Taguchi design of experiments, we saw that there is the most influential parameter is the orientation. And the reason for that is because of energetic point of view. And we also presented a heuristic model that showing these results. And in fact, you can see the microstructure and then estimate the dynamic mechanical properties. And this is how we connected between the microstructure, dynamic mechanical properties, and the scanning parameters. So thank you very much. And I want to thank my group and my supervisors. And if you want more details, you can find them in one of the 5 articles that comprise my presentation. So thank you very much.